morning, everyone, and welcome to our webinar. We've had a good amount of interest and lots of registrations from lots of customers, but also people around the globe. So good morning, good afternoon, wherever you are. Thanks for joining us today. We're fortunate today to have Dr. Predrag Micic joining us in presenting this topic. Most of you, I guess, would be familiar with Dr. Predrag. He's been around for a while. He's a familiar face across the industry. At conferences or pipe events. He's had lots of experience and influence across the pipe industry and the market. So we're certainly very fortunate to have him here today to benefit from his insights. Just a quick note, we will be at the APGA conference next month. So if you want to have further discussions in person, you can ask us more questions then. But in the meantime as well, if there are questions around this topic, do feel free to send through an email or give us a call. Just a couple of housekeeping items quickly. We are recording this seminar and we will be sending out links to the recording as well as the slide pack, so you don't have to take notes if you don't want to. Now the session, we've planned for it to run for approximately 1 hour, with the presentation taking about half that time. We can leave the rest for questions at the end. So in the meantime, please do send through any questions that you have on the Q&A. There should be a Q&A function somewhere in the bottom right. So send through the questions and then we'll get to them at the end of the presentation. So once we run to the 1 hour mark, feel free to log off if you have to go somewhere, but feel free to hang around as well if there are questions that run over time. So we'll hand over to Dr. Predrag. Should be a good presentation. Thanks, Predrag.
Thank you, Jonathan. Welcome, everyone. Jonathan mentioned a few names that they join in, so I have to say that whatever I share with you today is my experience and Qenos experience. I also learned a lot from you people there, and for the exchanges that we had over years. And I'm looking forward to the very interactive session at the end of this session. To learn how you feel about this topic, which is P1RC and relevance to future Australia, New Zealand polyethylene pressure pipes product standards. So it is quite an exciting topic. So this is the picture, just to know who is presenting. Not much to add to what Jonathan had already said, but handsome. And what we are going to cover today is the introduction to P1RC, where the RC stands for raised crack resistance. And this is the first time in 30 years that we have a new PE specification in standards introduced in international standards and published. So in this webinar, we will describe what this P1RC is, and we will discuss the changes in the standards, both international as well as implications to Australian product standards and specifications with the introduction of P1RC grades. And we will touch, not to a great extent, but enough on what some additional benefits the grades can offer to network operators. And we'll finish, as always, with conclusions and a question session at the end. So Qenos polyethylene is supplied to all market segments, rigid and flexible packaging and pipe applications. And our polymers, polyethylene, is used in products from milk to food packaging to water and waste management. And significant part of our production is dedicated to polyethylene made for pressure pipe market, this bottom right picture. And this is the topic of today's conversation. Sorry for a bit of a cough. I am just at the tail end of the COVID recovery. So P100RC is P100 with raised resistance to slow crack growth as an application most relevant pipe compound, pipe and pipe property. So whilst initial improvement focused on increased material pressure resistance, in the past 20 years, more focus has been on increasing pipe compounds or pipe toughness. So P100 had been introduced about 30 years ago. So the first 10 years had been bedding in that material in the standards, in applications, learning what to do with it. And once when we realized, when that was done, the industrial and international scientific focus was really on increasing the its toughness, which was the focused effort for the last 20 years. So considerable progress has been made in improving polyethylene resistance to slow crack growth. And this trend was primarily driven by increasing awareness over the time that the field experience showed that the pipe failures have been in a brittle mode. So the real risk to pipeline structural integrity in surface is failure due to slow crack growth, which is represented by the photo of the pipe failure in a top left corner, while the other two properties or potential pipe failures, which is overpressure, ductile failure, the photo on our right top corner, as well as rapid crack propagation type failure, have not really been experienced in the field at all with polyethylene pipes. And there was no any record so that can be traced back to either pipe design or material properties with this type of failure. So the application relevant property is a brittle type failure and slow crack growth of the pipe. So P100 RC usage is growing in the European market. P100 is certainly not a new RC, is not a new comer in the market. It has been used by network operators since 2007, as this graph shows. So the graph shows on the y-axis the market share of different pipe materials. This is in a kilometers of pipes, while the x-axis covers the time span going from 2007, when the P100 RC was first introduced in the market, till today, and maybe a few years going forward. And it is very clear, this is European picture, that the polyethylene, both P100 and P100 RC, experience significant growth at the expense of other materials, and P80 is nearly phased out. So, but the really remarkable growth was in P100 RC, which now currently takes about 30-35% of the total market share in Europe. And this trend is rising. This is even more remarkable taking into consideration there has been standards or documents that guides the use of this material. So this growth has been because the network operators must have realized the benefits that this grade offers. And the rationale behind this is really that the trenchless installation has been growing very rapidly in Europe, and this material has proven to be very beneficial to that sort of installation. So we cannot say for certain that the same trend for P100 RC market penetration seen in Europe can be simply assumed in Australia. We do have some specifics here, like the strong energy market, coal seam gas and mining, which are big users of polyethylene. But the concentration of population in a few megacities, as well as aging regional pipe infrastructure, makes EU experience and relevance to Australian pipe industry important to consider. So many of the pipe installations in the future will be in such high density populations with little tolerance for disturbance caused by, for example, trenching installation, and therefore there will be increasing trends towards trenchless installation, which makes the European experience quite relevant to Australia, and we see that in Australia. So we need materials with greater slow crack growth resistance for demanding application, and trenchless techniques are transforming PE installation. So the techniques like horizontal directional drilling, here on the photos, pipe bursting, swage lining, slip lining, they offer both installation advantages in cost efficiency and minimizing disturbance to urban and environmental areas where this installation takes place. But the open cut installation, like this bottom right picture, also can benefit from use of tough material, for example, by not having to use sand bedding and removal of the point loads due to presence of rock in the filling material, etc. So polyethylene in general is a very good material to due to its flexibility and toughness, but P100 RC in particular, given that it's really relevant here. So trenchless installations carry a high risk of damage to the pipe surface and the potential for slow crack growth and implication reduced service life must be considered and designed for. And we can see here a few photos from the field. In particular, telling is the bottom right photo, which shows the pipe coming out of the hole during HDD installation, and the clear score on a pipe or notch is visible. So it's a post-event, very hard to do anything with it. So the slow crack growth driven failure or brittle failure of pipe becomes then a critical issue because of this defect. And the last 20 years, as we said, made a concentrated effort to develop materials with enhanced slow crack growth resistance, and success in this field with particular P100RC with such a high resistance to brittle failure due to slow crack growth mechanism did create some complexities that needed to be sorted out in order that material gets accepted in the market. So it comes down to market application and standards. And why it is important to talk and have standards is that the gas and water pipelines have to comply with higher regulatory requirements, and operators only use certified materials. So till now, there has not been product standards for P100RC. And this caused uncertainty, regarding the performance of pipes made with such material. So complexity is really long testing time because of this property, and the high slow crack growth materials require long testing time in traditional tests, like notch pipe test, more than 1 year, and this is impractical. So there is a need, or there was a need, for a faster testing methodologies that allow us to be able to work in a real time, couple of days or a week by most, in being able to release the pipes and test them, so we have a quality system in place, QC, QA purpose. So, but we also needed methods that would induce various strange stress conditions on material, as we may expect to encounter in field during these alternative installation methods. So EN and ISO product standards for polyethylene pressure pipes provide guidance and regulatory framework, and there are 4 main standards, product standards dealing with polyethylene pressure pipes. These are international EN standards, European nation standards 1555, that guides how plastic piping system for supply of gaseous fluid. And there is EN 12201, which deals with water transport. And there is also ISO framework, International Standard Organization 4437 for the gas pipes, and ISO 4427 that deals with the matters with water pipes as well as drainage and sewerage. So these are the mother standards that we deal with. And the 2 committees that deal and make up these standards are in CN world, EN world is TS 155, and in ISO world it's Technical Committee 138. So in Australia, the same matters are dealt with PL 006 committee, which then governs all matters about Australian product polyethylene pressure pipe standards, which is AS New Zealand standards 4131 and 4130 for compound and pipe respectively. But the policy of standards of Australia is to base Australian standards on international standards to the maximum extent possible. And this is the benefit to the Australian economy by facilitating the international exchange of goods and services, but also international standards like ISO generally reflect the best practice and experience of industry and regulators worldwide. So we get all that experience. There's many more people in the world than it is in Australia. And hence, we tend to incorporate that experience in our own regulatory documents and standards. There is also benefits of participation in international certification schemes, which makes it much easier if the standards have got the same specifications, cover the same issue. So in Australia, high-density PE pressure pipes are governed by AS New Zealand Standard 4130 for pipe and 4131 for compound to ensure fitness for purpose. So although the structure between EN and ISO standards is different to Australian standards, the specifications and testing methods are the same. This is what matters. This is the trust of it. So specifications are outlined for pipe compounds and pipe itself in a table here. And the most important to mention is that all three systems, EN, ISO, or Australian system, they all require compound to be pre-formulated with all additives, including the carbon black. And three most important properties, which is classification or pressure resistant, MRS, what we called. And maybe I'll move my mouse around. You know, rapid crack propagation, as well as the resistance to slow crack growth, which is here in red, are the same among all these three systems. And in red, slow crack growth is the subject of P100RC and revision of EN and ISO in a future Australian standards to introduce P100RC. So P100RC standard development history. Standards get revised based on time, and this governs which standards get revised first. But there are other specifics that governs that. For example, it's usually EN standards get revised first, and then followed by ISO, and then followed by Australian standards. The practicality behind it, although the same people sit on committee, for example, EN and ISO, the people, they do the work. There is much less a number of countries in Europe that have to agree on this new change. So if the change goes through that environment first, then it becomes a little bit maybe easier to incorporate in ISO world, and then it flows over to the rest of us here. So getting publicly available specification of standards published is a long process, which require either very close to consensus like in EN and ISO, or effectively the full consensus in Australia between all involved parties. And for P100RC, the first effort started in 2009 when the past tense 75 publicly available specification for P100RC was published. But this was published by a limited number of people, limited number of laboratories. So it wasn't really accepted as a standard, or had no that weight behind it. And the real true document is actually only published in 2021, which is EN 1555, which was published with P100RC criteria. So what is it? 20 years, 15 years behind this first effort till that we do have the real standard with it. And what we have is ISO this 4437 ballot, as well as EN 12201 ballots are finished as well, and there will be progress. Unfortunately, we had a little bit of delay with these two ballots because the conveyor who passed away, who is a very dear friend to quite a few of us, Steve Beach. I just wanted to mention him here, but the world keeps going, and the work on this is going to complete soon. What happened actually between this first effort in 2015 to 2018? There was a really a very complex work done, led by German organization DVGW, which is organization that establishes standards and test protocols for gas and water pipe in Germany, and with the participation of quite a few other competent organizations. They developed the accelerated test for predicting slow crack growth. That was 2015 to 2018. And in 2018, then that work was actually discussed in those ISO and EN pipe committees, the TC138 and TC155, which then agreed on defined specifications. So first we needed to have the standard, the test, new tests, and they were the standards in their own right. Is that right? So they needed to be voted on and agreed on, and benchmarking, etc. And then from there, the people needed to agree what specifications describe the P100RC. That was all done, for the first standard to have this in 2021 incorporated. Now, Australia wasn't sitting dormant in all that time. So in 2015, we started to scope our own document specification, what describes materials with high toughness, P100, and that work started in 2015. It took us, even in this environment, 3 years to come up with what we call POP 16, which is industry guidance for high stress crack resistance P100. So we had something in place here in Australia in all that meantime, which we call P100 HSER, P100 with high stress crack resistance, which effectively is the P100 RC. So we had some guidance document that tells people how to go about it. But certainly all that describes here that the people only work on relevant properties, and it takes a long time for something to be published as a standard. So what are the changes in product standards with the introduction of P100 RC? So as I said, introduced and published EN 1555 and 4437 ballot finished 12201 EN for water. This ballot also finished. And Australian product standards revisions are expected to follow this guidance, as we discussed, for the reasons and the reasons behind it. And when that happens, in P100 RC gets put in our standards, POP 16 is expected to be phased out. So the changes in the standards will be from current having P80 and P100 classifications. We will get another classification in standards, which is P100 RC, which is how it is now in these international standards. So the new tests also will be present there, which are introduced for P100 RC, and these are the tests that target the slow crack growth specification. They won't be there for P80 and P100. This is just also very specific to the introduction of the new classification P100 RC. So what are these tests? The accelerated slow crack growth test for P100 RC. Actually, there are 4 additional tests that are introduced for P100 RC compound that were not required previously in product standards for pipe compounds and pipe itself. So the 2 tests, accelerated FNCT test and accelerated notch pipe test, are actually accelerated versions of the existing testing standards. We already had these test methodologies, but we needed accelerants, and what we see here is that they are accelerated with the use of the surfactants. So accelerated FNCT test is carried on compression molded plate specimens, so there is no influence of residual stress imparted on material during processing. That has an effect on the results. Accelerated notch pipe test, on the other hand, it's done on a finished article, which is pipe, which has got all these processing influences on the pipe. But there are 2 new tests. One is crack round bar, which is the determination of resistance to slow crack growth under cycle loading, and you can see it on the top right schematics. We introduced the cycle loading. It's done at the room temperature. So this is when I mentioned that there are tests that now introducing the different strain stress conditions as well that we may encounter in the field, and they can lead to slow crack growth, not just a static pressure. That could be, the big accelerant is also fatigue, the cycling strain. And there is a strain hardening modulus, which is the bottom right picture, which is sort of a tensile test, but done at 80 degrees. And this is the test that is proposed to be a QC or QA test. So these are 4 tests that will accompany the P100 RC classification there in the standards. So the P100 RC testing criteria was developed by DVG W coordinated program. That report is available for to purchase and to buy. It shows all of this benchmarking, etc. down. I think it's a very informative, good report. And what we can see that the criteria that's been developed and agreed, and all of that work took quite a few years to develop benchmarking capability of several testing institutions to perform characterization, because first they needed to characterize RC materials around to know what their performance is, and then to have quite a few testing laboratories that are able to do the same test. So the benchmarking was the most extensive that I have ever seen. And this test specification allow us now to have a QC, QA methodologies to make the product and test it that we know, but also in the field. But it will also enable the fast development times, because as you can see it here, they are not really too lengthy. The lengthiest one is 550 hours, which is about the month time, which is a significant improvement over 1 year plus, which was which was previously there, including in our POP 16, including in past 1075. That was there were criteria there before. Now we do have here much more practical approach to how to test these materials. They're very complex tests. So what do we do with these materials now, and how do we go about P100 RC designing? So in Europe, it's growing very, very hard again in trenchless installation. It gives you safety, of mind that you do have a material that is able to resist all of these imperfections on a pipe that may be they imparted during this alternative installation. In trenchless installation, damage may exceed the conventional allowance of 10% of the pipe wall thickness. Let's just elaborate on one of these scenarios. And if possibility of the significant external damage exists, then the potential for slow growth must be, of course, considered. And what we have in our standards is some guidance for the use of the design safety factors, not safety, design factors. They used to be safety factors. Now they're called design factors, which say, okay, if the installation is open trench, I do not need to do much about it. But if it is directional drilling, I do need to consider that real risk of failure due to pipe notch. Hence, I need to use the higher design factors. So the plastic pipe industry historically adopted many proven practices used in metal pressure pipes, and by extension, there has been strong emphasis on managing risk with conservative design factors. And the design factors in standards go back to that, what we have them in standards there, to this prescriptive time. So prescribed values for design factors are meant to deal with perceived risk of pipeline failure and consequences of that failure. And I stress perceived risk. There is really no scientific basis for design factors, values. And I think standard recognizes that, both perceived risk and scientific uncertainty, by making design factors informative rather than normative. And we have that in our Appendix C in AS 4130. If you go there, that table with the proposed design factors is actually informative, not a normative part of the standards. And it is very important to talk about it, because the standards and national codes also have changed over many of the recent time, and the regulations are now not design prescriptive. They're explicitly goal setting and performance based, allowing provision to design pipeline based on a risk-based design. So the real risk, rather than managing the risk just by increasing the pipe wall thickness, that may not be the best integrity safety measure, for the risk that exists there. And for example, for horizontal directional HDD installation, the real risk is the presence of notches on pipe surface that may have been incurred during installation. These notches present potential points for slow regrowth and progress to brittle failure, but also they can be deeper than 10% of the wall thickness as prescribed in installation or guidance document. But many of our current standards, 4645, you name it, code of practice, they already have now two ways to design: prescribed way, and they have a risk-based design that you can choose to follow. So the notch pipe testing, as we said, that in this case, we're talking horizontal directional drilling. Maybe a presence of the notch is representative of pipe installed and damaged during aggressive installation method, like a HDD. And for PE compounds, we do have a test for that. Resistance to slow regrowth is measured by notch pipe test according to ISO 13479. The test is done on SDR11 pipes, notching standardized procedures up to 20% of the pipe wall thickness, and then the pipe is pressurized to 920 kPa, which is about the right pressure that the stress that they see in field at 80 degrees, and the time to brittle failure is recorded. But the test programs with notches deeper than standard prescribed 20% of the pipe wall thickness demonstrated that the P100 RC pipe with a notch depth of 30% was considerably outperforms in this relevant test the standard P100 pipe with a notch depth of 20%. So if P100 RC is specified to guard against brittle failure as an integrity measure, a lower installation factor possibly can be considered. So while in a prescribed design, in this informative design factors, we can have for directional drilling 1.2, which gives us the wall thickness safety, to guard against it. If we use the right integrity measure, which is the material with higher resistance to that notch, we may be able to drop the design factor to 1, for example, and based our design on a fitness for purpose design where P100 RC pipe is specified. So that testing program certainly supports that, and this means that if you use P100 RC, that the risk associated with slow crack growth can be dealt with in this way. So it's just one of the examples. But there are many ways how P100 RC and this increased toughness, because as I said, this is the whole industry worked on, because it is a relevant property, can contribute to our designs and cost effectiveness, and increase in service life and savings in pipe and construction cost can be achieved with P100 RC in all areas. So we can have a lower cost in installation cost because of the bedding or spoil screening. We have high risk installation, trenchless, and potential for the reduction of welding time, if we are not over designing our pipes. And very often I can see pipes of PN25 in horizontal directional drilling appellation. The pipes that will operate at 8 bar, we're using PN25, SDR9 or even thicker pipes, so we're building that through the wall thickness, which is probably not the best integrity measure. In a surface life cost, we have reduced failure rate, more extensive use of squeeze off, no problem with this, and longer design life. And in the pipe cost, more effective design solution for reducing risk of brittle failures when compared to increasing wall thickness. So there's an increasing wall thickness that really comes from the metal pipes in the past. And with our education, our understanding of the real risk, not a perceived risk, we may be able to design our pipes a little bit better. And this is recognizing standard with introduction of fitness risk-based designs opportunities. So in conclusion, it's really that failure by slow crack growth is the main threat to I'll just move Jonathan a little bit so I can read off the screen. That's it. Is the main threat to P pipeline long-term integrity, and of particular concern in trenchless installation. So all we are talking here is about P100 RC. It's a really targeting trenchless installation. Really, I mean, there may not be as many benefits in an open cut as it is in trenchless, and this is where we also it's been targeting that part. P100 RC is specifically designed for trenchless pipe installation to increase service life and confidence to tackle these difficult ground conditions. And P100 RC provides a built-in safety factor against slow crack growth failure and may be used for fit-for-purpose design of pipes with lower installation factors. But if you don't feel confident about it, it still provides you safety of mind that your material that you use there can deal with all these conditions. Even if you don't feel that you need to design. Here we go. So ISO this technical committee 138, which is plastic pipes, fittings, and valves for transport of fluid, and as well international EN, European nations, TC 155, plastic pipes and ducting system agreed on testing methods and specifications for P100 RC, and EN 1555 for gas was published in 2021 with P100RC specification. 4437, which is ISO for gas transport, finished this balloting stage and has P100RC included. So that ballot is finished, and I think it's processed. Actually, it just needs to be finalized. EN 12201, which is for water, revision agreed to follow EN 1555 and to add P100RC materials, and the ballot stage is complete in 2022. PL006 committee looks after product standards for pressure pipes, polyethylene pressure pipes and compounds respectively in Australia, and it's expected to follow ISO and EN taken approach and introduce P100 classification to complement P80 and P100 classifications already present in that standard. And future revisions of AS New Zealand standard for 4131 compound and 4130 for pipes are expected to follow this taken approach and to include P100RC when the time comes for their revisions and when we are ready to do that, which is likely from what I'm hearing to be sooner rather than later. And POP 016 and P100 HSER specifications that we have are expected to be made redundant once when Australian standards incorporate P100RC. So this is effectively bringing me to the end of this presentations when, as I said, we just, I think, just summarized what's happening there in the world, both in how this material had been accepted, as this is really remarkable without having a regulatory framework around it. And now with the framework which is in place, it is expected that this material will grow even more. The trenchless installation is growing. The relevance to Australia is very high, and hopefully you're getting a feel from here where we are with as I said, mostly regulatory frame around this material, which was missing till now.
Thanks, Predrag. That was quite a bit of information, so I'm sure our attendees are still digesting it. Maybe I'll kick off with a couple of questions. So you've really given us, I guess, an appreciation of how long and extensive the process is to get something included in the standards, this P100RC included. Now, you've made some indications of, like we expect this to happen soon, but do you have an idea of the timeline or timing of when the new classification will be introduced into the AS standards?
Well, it's a good question. As I said, it's very hard for me to look into the future, but I think what was important, the milestone was that one of the recognized product standards in world that Australia follows, the same, it gets published, and this is EN 1555. The rest of the standards now will follow. There is no expectations that ISO water standards or gas standards, they are already in a ballot stage, wouldn't be the same specification. So in a sense, that the hard work has been done. So what happens now to Australia is for a PIPA committee first, PIPA, to sit down and work out how we can migrate what we learn from there into our standards. I expect that there won't be too many. We already have POP 16 in there, so there was a recognition that these materials are there to stay. Now, this is very hard to doubt, and that there is a benefit to the community. So I would expect that this work will start very soon, and it will progress, without too many waves around. So I'm hearing from my PIPA committee members that they're keen to work on that soon, and my guess is it's already the end of the year, but we don't have to come up with the specifications anymore or with the testing methods. So all we have to agree on something, and that may happen very early next year. Sometimes next year. That means that PIPA might agree, then we will bring that to PL006. That happens once, as a revision. So I need to see when the product standards are meant to be revised, but it doesn't mean that we have to wait for that. We can include these specifications as amendment or something like that but it will happen, as I said, over a course of 1 to 2 years. Let's say 1 year. I would aim for the end of the next year.
Okay, thanks, Predrag. You're going on the record and promising that it'll be 1 year.
Well,
Very
I'm only
bravery.
one member of that whole community. That there is a process to follow, and this is a very high integrity process, so it needs to be followed. But technically, there shouldn't be much disagreement. And that's important.
Thanks, Predrag. Appreciate that. One other question. I guess given the growth of P100RC in the European market, even without the standards being introduced to date, I suppose what are the real benefits of introducing that change in the specifications for P100RC specifically, and what is your expectation of its adoption in the Australian industry and market?
Well, hopefully I presented here some potential benefits that one can take. As I said, at this point of time, we measure a lot of our integrity of the pipeline, polyethylene pipeline, its safety and operational integrity. We measure we ensure with wall thickness effectively. It may not be the right integrity measure for the risk that we have there. So the slow crack growth type of failure is a very different mechanism to or a pressure or ductile type of failure. That they have nothing in common. They're two different mechanisms. So we need to have a right integrity measure to guard us against the slow crack growth. And this is the toughness of material, which is what this material is about. So there may not be a need to over design the pipes and through the wall thickness increase to guard against the failure, if it is not maybe the most effective way. So there is, for example, issues with the squeeze off and other stuff. So what this does is not to abuse the pipes, but it certainly gives you opportunity to handle them in a rougher way, which is what the trenchless installation maybe do. So you may be able to really drill the pipes through rock areas. You may be able to use as dug feel as well in open cut, to load on there, the things that have got rocks and other stuff that will pose the danger of brittle failures and that sort of stuff. So due to the point loading. So this is the material that can take that and not develop into the brittle failure. But at the end of the day, it's always the industry that teaches us what they can do with it. We give them something, but how they're going to extract the value out of it, it's really up to the industry, as they learn and adopt this material, etc. So, just the fact that in Europe that got a 35% now the whole market share, in the pipes installed, it tells that people see the value in that material. How it's going to get adopted in Australia, I think the same. I think it will grow, over the next years with the existence of the standards quite considerably. Having said that, there is nothing wrong with the P100 material, horses for courses. This is the material that we would really say it's suitable for trenchless installation. All right, there is no problem with P100 in trench installation or even in some trenchless installations.
That's right. Appreciate that, Predrag. A couple of questions popping through. Is this P100RC pipe currently being marketed in Australia? I suppose that's maybe we'll just quickly address that one, Predrag.
Yeah, well, as I said, we had that P100 HCR guidance in place while we didn't have standards. Now we have standards. The Qenos material HCR 193B is P100RC materials. We have completed all this testing which are required to conform to P100RC specifications as it was in this presentation. So we do have a material which has got all these tests complete and done. So once when the standard gets published, that will just be P100 HCR 193B is P100RC, fully conforming, all done. So yes, we do have them in Australia, but there are other people who would have also met these requirements. The people from our competitors, I would say, they can offer this material as well. So you're not tied up with Qenos only or something. This material has been around for 10 years plus. So there will be few companies that are able to make it, but it is a really high-tech material.
That's right. And Predrag, I suppose it's worth mentioning that our material, the HSCR, is undergoing these tests as required by the specification that you mentioned, and
complete, all done. We have that dossier put together, so that they're done. Yes, and we met all requirements. Yes, by HCR 193B.
That's right. It's quite a rigorous testing
yes.
process, and so it's good to have that
Yes.
right away. All right, a couple of other questions coming through. Aaron's asking, are higher grades being investigated at the moment? P112, P125, etc. We're being asked to review these, but they aren't recognized by the Australian standards at the moment. And maybe a second parter, is calling P112, P100 okay, just because the standards don't recognize it?
Well, it's I'll answer that question. As I said, P125, let's put me that straight away. It won't happen during my lifetime. It's hard one to make. We all work on it, but it's a matter of trying to learn. But P125 is a stretch for polyethylene. And what you need to have is these standards that define P125. So when we had when we developed P100, that we realized that because it operates at higher pressures, there could be rapid crack propagation. So if you look into P80 material, it doesn't have rapid crack propagation test. P100 has. For P125, we may learn something new. So it's a really big time in the future if it is even possible to do it. P112 exists around, it gets marketed, and maybe it is good to address it this way. As we said, it's a technical presentation. Okay, so I concentrated the effort by international communities over the last 20 years really got us to this point to have P100 RC. So there is no such effort for P112. There is no working project to do anything like that for P112. So the rationale is really following is that the benefits of P100 RC relate to trenchless installation. So due to the risk or of the pipe to have brittle failure due to all these imperfections that can be put on pipe during installation, notches, point loading, they're expected to happen during trench installation. So hence, there could be a slow crack developing over that, and therefore P100 RC is addressing that real risk, I would say, and that's why it got taken up to an extent. On the other hand, benefits with materials with higher MRS, like P112 versus P100, for example, relate to the pressure bearing capabilities. That's right, ductile performance. And they could be relevant to open cut method. When you do not have slow crack growth imperfections, you don't have, you have a sand laying, you cut the sides of the notch, so there is no anything, poking in the pipe, etc. So maybe somebody can extract some value there, remove, with very careful installation, but there is no really clear relevance of the ductile performance and higher MRS to the benefits in trenchless installation. Nobody can make that correlation. They're not the same type of failures, so there is no benefits of that. So any potential design really that the higher MRS, like with P112, may result in some slight downgauging in open cut method, open cut installation. There could be somebody maybe good enough, through this risk-based design to extract that. But these are really minute benefits, because the pipe sizes we are dealing with, if you do the small, wall thickness reductions that P112 can maybe extract, are really pale in significance to what the cost benefits of trenchless installation is versus the trench installation. So the international community and rationale do not see there the need to be able to develop and work on P112. There is no working items anywhere on that. This is just But if somebody can extract any value out of it, good luck. But it is not what it is not what these committees would be working on in future, to my knowledge.
Okay, thanks, Predrag. Now, just on the testing methods, so the accelerated FNCT method that you indicated, how does that differ from the current slow crack growth testing mechanism that's already required?
The slow crack growth mechanism, we do understand. It's got crack initiation, and then it's got crack propagation parts of it, and the crack initiation is different to crack propagation, etc. So what they're doing is they're accelerating the current test with the use of effectively what the surfactants are. And these surfactants, what they do is they manage to reduce the surface tension, which is the driver for crack propagation part, etc. So they're accelerating the current test, as I said, full notch creep test and accelerated version on notch pipe test. But in all these tests that DVGW did, they've done these correlations. So they were done benchmarking between the standard notch pipe test, which is done in a water versus the notch pipe test, which is done in an accelerated environment. And they would do all this benchmarking to derive these correlations to come up with a credible number that describes the P100RC. Let's say 300 hours in accelerated notch pipe test. If you have taken that same pipe and you've done it in the water, it would last for a year. So, but that needed to be done across the different labs, etc., etc. So that's why that work took 3 years or longer than that to be able to establish these correlations, to be able to trust the data. That's why if you go to this report that we have in that presentation, you can buy it, you can see all these correlations, how they come. It's like a book, but it's worth reading for someone who wants to have confidence that these accelerated methods are credible methods.
All right, and we have a question as well, Predrag. What are the differences between P100 HSCR versus P100 RC from the manufacturing perspective? I suppose that's really just a branding or marketing thing. For the Qenos grade, we've called it P100 HSCR, but it's effectively the same thing as P100 RC. It's just a difference in terminology.
That is difference in terminology, and there's a difference in testing methods now that it will be present in standard versus what it is already in POP 16. So in POP 16, we do have accelerated methods that that were developed in the past, but some of so we still have there four requirements, etc., etc. But if you look into the specifications, how many number of cycles somebody needs to do, or the time it lasts, etc. You have in POP 16 still notch pipe test, which is required to go for 5,000 hours based POP 16. Now in the standards, you have notch pipe test accelerated version, which is 300 hours. So we do not have accelerated version of that in POP 16. All right, so it is the POP 16 was done in Australia with the best knowledge on the day, and it was, I think it's very credible document, but it is still impractical document because it doesn't really have a method to do QC and QA, etc., which is what all that got addressed by this comprehensive DVG-DW program. So the POP 16 really should become redundant at some point of time. It was a really great document on the day, but what we have now, it's much more sophisticated and much more effective document, and that does reflect that when these people get together, somewhere in ISO committees and EN committees, they do come up with a good work because they accompany all of these inputs all around the world. The same materials, P100 HSCR Qenos, great, that met all POP 16 specifications, now have met all P100 RC specifications. But that doesn't have to work for all grades, because the tests are now different. and the specifications, the time requirements, etc., is different between POP 16 and what RC requirements are in standards. So someone who wants to claim P100 RC cannot just claim it based on POP 16 conformance. They need to go and do all this testing as required by standards, which is what we have done.
Thanks, Predrag. We have time for one or two more quick questions. So just keep that in mind. We'll have a question around temperature, I guess temperature applications, high and low temperature applications versus normal P100. Is there a minimum and maximum temperature application for P100 RC?
It's an excellent question and a very practical question, and this won't change to normal P100. Okay, a lot of temperature, durability at the higher temperatures. The molecules give you that, but also additives give you that. So a lot of resistance to higher temperatures come to the additivation, and it's a very specific know-how there. How you make sure that all these molecules that gives you all this strength do not change due to the degradation at exposure at high temperatures over a long time, which was one of the problems with test at 80 degrees for 1 year. After 1 year, the polymer starts to degrade at 80 degrees. So what you need to do for use of polyethylene at higher temperatures are specific grades which exist, which have got all these molecules that we require that gives you RC, but they also have additives that provides durability and resistance to degradation at these high temperatures. And this is in particular relevant in contact with water. It may be less relevant to contact with gas. Gas is safe. It is the water that does that to an extent. It's actually water is more demanding on polyethylene than it's a gas application. Yeah.
All right.
So you need to come for the specific grades, and they exist.
Okay, and I'll just read this. Not really a question, Angus, but I'll just read this out. We have adopted HSCR in our network, Water Corp, Western Australia. For a number of years now, it would be of interest for us to see the comparison of HSCR versus P100 RC tests used to demonstrate compliance with the respective grade classifications. I suppose I'm wondering if the question here is, I hope I'm not putting words in your mouth, Angus, but is there some sort of back compliance that's going to be required for P100 HSCR versus RC in the future?
This is not a question for me, isn't it? You're still waiting for Angus to answer.
No, I suppose it's more of a comment, like at some point.
I think to answer that, absolutely. I think Water Corp has adopted that. It was an early adopter, and that's great. So P100 HSCR, at least from Qenos, great HCR 193B, which Water Corp has got experience with, now has demonstrated all requirements for 2P100 RC as per EN requirements and ISO requirements. The testing has finished, so all these reports can be made available to compare. As always, there has to be transparency there. I can't just say we completed it. All these reports have been done in the labs which are certified to do that overseas, etc. There's very little you can do in Australia with these very specific tests. And what we are doing as well, we are implementing in our lab a strain hardening method. We are just in the process of doing that because that is going to become a QC test for us, as well as we keep making this grade going forward. So all these reports are available. That's no problem. We can do it. Yeah.
All right. Thanks, Predrag. Angus, I hope that answers your sort of question. So I think we'll call it time there. It's been about 1 hour. So thanks to everyone who's joined us. Thanks, of course, Predrag, for that informative discussion. We will be sending out the recording and the slides, and we hope to see a few of you at APGA next month. So thanks everyone for your time today. Appreciate it. Thanks, Predrag.
Thank you, guys. I appreciate that. I appreciate the opportunity.